Now, in this video, we will going to discuss about analyzing virtual product models. So, computer-aided engineering is a term used to describe the use of computer software in the product engineering process. From design and virtual testing with sophisticated analytical algorithms to the planning of manufacturing. CAE solutions support the engineering process, allowing designers to perform tests and simulations of the product's physical properties without requiring a physical prototype. So that means we are doing the virtual prototyping. That means in the earlier stages we used to produce or to fabricate and to get the prototype model and then do the analysis on those models, and then finally we used to get the prototypes. But today, since the advent of softwares which enables the company to go for the process wherein you're going to make the design and then do performing of testings and simulations have been done by using virtual. So that is the reason why, which is called virtual product models. CAD is used to create a geometrical product representation within a virtual environment. CAE allows a deeper analysis of the product. CAE finds applications in engineering fields like fluid dynamics, kinematics, stress analysis, finite element analysis, etc., typically where product development is concerned. So basically, when you want to develop a product, first we have to do the designing. Once you do the designing, then we have to do the analysis, and that is the analysis may be of different types: fluid dynamics, kinematics, relative movements, then the stress analysis and the finite element analysis, etc. So this is everything has been done by using virtual, and that means by using the software. Throughout the virtual development cycle, CAD and CAE go hand in hand. So CAE helps to reduce the number of physical prototypes and experiments and optimize the components in the design phase to develop better products faster. Now we're going to take up the first one, the finite element analysis. It is the simulation of a given product or any given physical phenomenon using numerical technique called FEM. So this is finite element methods. So basically these finite element methods will going to adopt the numerical technique. The technique is used to calculate stress, deformation, thermal load, structural dynamics, or NVH, that is the noise, vibration and hardness, and predict the behavior of the product in the physical environment. FEA helps design engineers to review and optimize the design at any early stage, thereby saving time, energy, and money involved in developing the product. Various softwares like CATIA, Hypermesh, ANSYS, etc. are used for the purpose. So basically FEA software which we are using here to be a CATIA, we're going to use for the Hypermesh and also the ANSYS. Basically Hypermesh and ANSYS, Hypermesh is used for meshing the product and then do the analysis by using the ANSYS software. FEA works by the discretization, that is break down a large structure with the high degrees of physical complexities and mathematical discontinuities into more manageable sections. So basically FEA works under the principle of discretization. That means taking a single product and dividing into multiple points so that you will going to get very minute complexities and the physical complexities with the mathematical discontinuities into smaller, more manageable sections. The mathematical model or geometrical model extracted from 3D CAD model is discretized by the FEM, resulting in corresponding numerical models. So that means we are discretizing a 3D model which has been developed by CAD and then discretized to smaller, discretized by the FEM, resulting in corresponding numerical models. Discretized equations are solved simultaneously and the results are analyzed to determine how the larger structure will respond to the external or internal stimuli. Boundary conditions of loads such as force moments, restraints that is for bearings and fixed parts, material characteristics, temperatures and other factors are defined directly by the FE program, the finite element program. That means the boundary conditions can be applied of loads. In case of loads, it will going to be forces and moments. If it is the restraints, it will be bearings and fixed parts. Mathematical characteristics, the temperatures and other factors are defined directly in the finite element software. Next comes with the computational fluid dynamics, which is CFD. It is used to refer to a wide spectrum of numerical methods used for virtual analyzing and predicting complex 3D time-independent flow phenomena related to products. For example, simulating and analyzing the flow of gas over the turbine blades, temperature distribution in a heat exchanger, etc. So basically, computational fluid dynamics, which is used for the flow of gas on the turbine blades and the temperature distribution in the heat exchanger. The analysis approach in this regard is similar to FEA, except the software used being different. The data transfer for 3D CAD model into the CFD program is performed by the standard data format, which will be STEP or IGES, and the boundary condition for the calculations are defined by directly in the CFD model. So basically, the CFD model is used for flow of gases in the turbine blades, and what will going to be the temperature distribution in the heat exchanger. For such type of applications, we are using CFD, and it works under the very similar to the FEA, finite element analysis approach, wherein the 3D CAD model is being imported, or the data transfer from the 3D CAD model into the CFD program is performed by the neutral standard format data, which is STEP or IGS, and the boundary conditions are applied directly in the CFD program. Solvers like CFX, Fluent, Nastron, etc. are the few softwares which will going to be used to conduct the analysis. The next one is multi-body simulation, which is called MBS. It is a computer tool with which multi-body systems can be simulated using the computational method. It consists of stiff bodies or mass points which are connected with each other or the environment by joints, that is the kinematic constraints, and are by specific force laws. They are very suitable for modeling complex inhomogeneous structures such as full vehicles, and particularly for low frequency range of the motions. The boundary conditions such as force, torsional moments, masses, moment of inertia, degrees of freedom of movement are directly applied by using MBS program, which is multi-body simulation. The separation of the local distributed parameters into discrete parameters like mass, inertia, stiffness, damping leads to the physical discretization of the product model. So this is how we can use the finite element methods, that is FEA, the computational fluid dynamics, and the multi-body simulation. In our next video, we will going to discuss about the production planning and control, which is called PPC. Thank you.